In the past decade, weather forecasting has undergone a quiet revolution, not through better physics but through better learning. Data-driven models are now matching, and even surpassing traditional numerical weather prediction systems in accuracy, speed, and scalability. But as these models grow larger, more complex, and more expensive to train, one critical question emerges: how should we scale them? This isn't just about throwing more compute at bigger models. It's about understanding the laws that govern how performance improves with data, parameters, and compute. That's exactly what we're diving into today: the scaling laws of global weather models, based on a groundbreaking cross-model analysis of 5 state-of-the-art AI weather systems: Aurora, GraphCast, Pangu, SFNO, and AIFS. Why scaling laws matter in weather forecasting. Scaling laws are not new. In language models like GPT, we've seen that performance improves predictably as you increase model size, dataset size, or training compute, following power law relationships. These laws let us answer practical questions. Should I train a bigger model or collect more data? How long should I train? What's the optimal trade-off? But weather prediction is fundamentally different. The atmosphere is chaotic. It's governed by physics, not grammar. It predicts hundreds of correlated variables: temperature, wind, pressure, each with its own physical behavior and predictability. And unlike language, where a model can learn patterns from text, weather models must learn dynamics from massive reanalysis datasets like Aurora 5, which contain 40 years of global atmospheric observations. So can the same scaling laws apply? And if not, what does work? Let's start with the most surprising finding. Across all 5 models, increasing width consistently outperforms increasing depth, even when the total number of parameters stays the same. You might expect that deeper models, with more layers, would capture more complex atmospheric dynamics. But here's the twist: wider models achieve lower validation loss, sometimes significantly, while being much shallower. For example, in Aurora, a wide configuration with 384 dimensional embeddings, and only 3 to 5 layers per stage, dramatically outperforms a narrower version with 128 dimensions and more layers. Same parameter count. Same architecture. Just wider. The same pattern holds for GraphCast, Pangu, SFNO, and AIFS. Even at a depth of just one message passing step, GraphCast performs well. SFNO's Fourier blocks achieve high accuracy with a single layer. And AIFS, despite using deep transformer stacks, shows diminishing returns beyond a certain depth. Why? Because 6-hour weather dynamics are well approximated by linear or shallow nonlinear operators. The atmosphere's short-term evolution doesn't require deep sequential reasoning. Instead, it benefits from high representational capacity, the ability to encode complex spatial and vertical relationships across the globe. This is a fundamental divergence from language models, where depth matters more. In NLP, deeper networks can learn hierarchical syntax and semantics. But in weather, the physics is already encoded in the data. The model's job isn't to reason. It's to learn the underlying operators that map initial conditions to future states. So the takeaway? For weather models, prioritize width over depth. Build wider, not deeper. Now let's talk about data. How much does training on more data improve performance? The answer lies in the data scaling exponent beta, where validation loss follows LD equals alpha D dash letter 1D 5D. A higher beta means you get more performance gain per unit of data. And here Aurora dominates, with a beta of 0.51, significantly higher than the others, ranging from 0.3 to 0.46. What does that mean? If you increase the training dataset by 10 times, Aurora's validation loss drops by up to 3.2 times. That's an extraordinary data efficiency. Why? Aurora's unified 3D tokenization preserves vertical atmospheric coupling, meaning it treats the full atmospheric column as a single unit. This allows it to learn global dependencies more effectively than models that split variables or process them separately. In contrast, Pangu splits surface and upper air variables, which may introduce artificial boundaries. GraphCast's message passing mechanism, while powerful, struggles with data efficiency due to communication bottlenecks. So Aurora isn't just fast, it's smart. It extracts more signal from every bit of data. Now here's a crucial shift in mindset. In language models, the classic wisdom is, for a fixed compute budget, you should scale parameters and data in tandem. But in weather, the story is different. Our compute-optimal analysis reveals a surprising truth. Under fixed compute budgets, extending training duration yields greater performance gains than increasing model size. Why? Because many models are undertrained. Even large models like Aurora and GraphCast haven't fully converged to typical training budgets. So doubling the training time, while keeping the model size fixed, gives you more benefit than doubling the parameters. This is especially true for models like GraphCast, which suffers from poor hardware utilization. Despite being smaller, it only uses 0.017% of H100 GPU peak performance, about 2,000 times less efficient than Aurora, which reaches 37.2% utilization. Why such a gap? GraphCast's GNN-based message passing is memory-bound and poorly optimized for modern GPUs. It's stuck in the communication bottleneck zone, where data movement dominates computation. Aurora, using attention-based transformers, leverages highly optimized cuDNN and flash attention kernels, making it far more efficient. This reveals a critical flaw in classical scaling law analysis. It treats compute as a static resource, ignoring wall clock time, hardware utilization, and engineering reality. So in practice, don't just scale up. Scale smart. For real-world deployment, smaller models trained longer beat bigger, undertrained ones. And now the final twist. Not all weather variables scale the same. We looked at two key variables, 10 mu wind and 2 m temperature. Aurora achieves the lowest RMSE for U10 across all dataset sizes. It's the best at predicting wind dynamics, likely due to its strong spatial modeling and attention mechanisms. But for 2 m temperature, GraphCast takes the lead, outperforming even Aurora. It converges faster and achieves better accuracy at smaller scales. This means the overall validation loss is only a rough indicator of performance. A model that wins on average might be terrible at predicting temperature or wind. So if you're building a model for flood forecasting, you care about precipitation and wind. For aviation, you care about wind shear. For agriculture, temperature extremes matter most. This suggests a new direction, variable-specific tuning or even hybrid modeling, using different architectures for different variables. So what do all these findings mean for the future of weather modeling? First, design for width, not depth. Wider architectures unlock higher representational capacity and better performance at fixed parameter counts. Second, prioritize larger datasets. Aurora's data scaling efficiency shows that more data leads to faster, more robust learning. Third, train longer, not bigger. For fixed compute, extending training time beats increasing model size, especially when hardware utilization is poor. Fourth, don't trust the average. Performance varies wildly by variable. Optimize for your specific use case. Fifth, engineering matters. A model's theoretical efficiency is meaningless if it can't run efficiently on real hardware. The future of weather forecasting isn't just about bigger models. It's about smarter scaling, understanding the unique physics, data, and hardware constraints of atmospheric prediction. We're no longer just simulating the atmosphere. We're learning it. And with these scaling laws, we finally have a roadmap to build models that are not just powerful, but practical, efficient, and truly predictive. So the next time you check the weather, remember, behind that forecast is a model that didn't just get bigger. It got smarter,